Hello, can you hear me? Hello, you have to unmute yourself.
Hello.
Yeah, can you hear me?
Yeah, sir.
Have you read anything in the gravitation chapter?
Yeah, sir.
What have you read?
So in the beginning, he's explaining how how they discovered the gravity or the gravitation force. Uh, then then they discuss about what the force is, like the GMM by R square. Uh, then they
Till where
discuss.
have you read
I read the chapter.
the whole thing?
Yeah.
Did you understand the field and potential part?
Some the field part under that they had derived the field and potential for a few objects. For the sphere, it was very confusing.
Okay. First of all, start off with Newton's law of gravitation. And that says that if there are 2 point masses m1, m2 separated by a distance r, then both of these masses will attract each other with equal and opposite forces. This force is the force of gravitation.
Right,
The force of gravitation magnitude will be g m1 m2 by r squared.
right,
And obviously the direction of the force, if you define your r vector from here to here, this is your r vector, then the force vector will be written as minus g m1 m2 by r square r unit vector. The
right,
reason there is a negative sign is because r vector is on this side, but fg is in this side,
right.
right?
Yeah,
This law is valid. This law is valid only for point masses.
right,
You cannot apply this law for in general masses like extended bodies and all. The
right,
problem is that there are so many point masses in that, right?
right,
Each point mass will attract the corresponding point mass here with some force. You will
right,
have to do vector sum of forces, sum up all of these pairs and all of these pairs, then only you'll get the total force.
right,
Which is going to be really difficult if there is a continuous body, there are infinite points. You cannot keep doing the infinite sum of vectors.
right,
So we have to come up with a new method to be able to predict what is the gravitational force between two objects which are not point masses, right?
right,
So for that, he had to invent calculus. So Newton knew that, okay, this law will not work if I have to calculate the force between Earth and Sun, for example. So in order to predict the motion of Earth and Sun and the gravitational pull there, you will have to figure out how to handle collection of point particles, right?
right,
The mathematical method that he figured out was calculus, and we will be using that extensively in this chapter to find the field and potential and things like that.
right.
So, first of all, one important idea here is what is gravitational field and why do we require a concept of field? What is gravitational field?
Uh,
So,
oh yeah.
tell me,
It's like the area of effect of the gravity around an object.
but gravitational field is not the area, it's not the space.
Like um, you assume that there's a space around the object where this gravitational field acts, and any object inside that field will have a force on it in the direction of the object.
The direction of the field.
Yeah, the direction. Yeah,
If there is a mass m, we are going to say that the mass m creates a field at all points in the universe.
right,
No matter where the point is, due to the mass m, there will be some field at that point.
right,
Gravitational field is such that it is always going to point towards the mass.
right,
What you need to figure out is what is the strength of the field and what is the direction of the field due to the mass m at each of these points. If you know that, if you know the vector field here, everywhere there will be a different vector field because the magnitude of the field will change.
right,
The distance between all of these points is not the same, so the magnitude of the field keeps changing. Also, the direction of the field also keeps changing because every time field is directed towards the mass, right?
right,
So once you know your vector fields at these points, gravitational field, then you can say that if I bring another mass, capital M here, the force that that mass will experience will be capital M times the field at that point.
right,
So in that sense, the way we define gravitational field is force exerted on a mass placed at that point divided per unit mass, right?
right.
And if you see here, you will have to take the case that limit m tends to 0 here. You have to bring a really small mass there.
Right.
Why do you have to take that case?
Because we want to find out the whole field regardless of the mass of what object you're bringing.
No, that's not the reason. The reason is slightly different. The reason is that if you bring another mass into the picture, automatically it will distort the existing field here,
Right, yeah,
because it will also create its own field.
right,
So if you bring another mass into the picture, technically the field at this point and this nearby points has changed a little bit.
right,
And
yeah,
it is not the original field that we are talking about.
right,
So we want to keep the mass that you bring in as small as possible.
right, yeah.
1 second, hold on. Okay, so this is the basic meaning of field, but one more thing that we have to understand is why do we need the concept of field? Why do we need idea of field? Because anyway, if there was a mass here and another mass here, we could have predicted force between them by simple gravitation law gmm by r square minus r unit vector, right?
Right.
So why do we have to write it like this? And later we will say that the E at that point is, you know, that it will be defined as minus gm by r square, right?
Right.
So why do these two steps when we already had the Newton's law of gravitation? Why are we introducing also the idea of field? What is the benefit?
It's so that when we discuss for the extended objects, the field is a better way to find it rather than using the Newton's the equation.
No, it is not better. How is it better? Because ultimately you will do the same integration in field also. You'll have to do that in force also. Like even if there is an extended object, If you had to calculate the field at this point, it would be the same thing. You'll have to integrate the field, right, to each small mass.
Right.
The integration doesn't change in complexity just because you have replaced E with F.
Right.
If you had to calculate force exerted on this mass due to an extended body, you would have to still do an integration involving all the forces.
Right.
Even for field calculation, you still have to do the same integral. It's nothing much has changed there. There is no simplification of effort to go from F to E. That's not the reason. Because actually, if you see F, the only difference between F and E expression is an extra mass, right? Doesn't change much.
Right.
So what is the reason we are talking about the field concept at all? Why introduce a field thing?
Maybe because if we are looking from one object, then the field will only show you the forces like uh, that. If you just use no.
So the reason is that when Newton was discovering his principle of gravitation in 1667 or so, that time nobody had seen any force which could affect bodies at a distance. All the forces that people had seen so far were forces where you could push or pull or twist or do something. It were all contact forces. All the forces that man had seen by till then were contact forces which could be understood by people. But now he is going to make a prediction that okay, Earth is going around the sun because of a force exerted by the sun across 150 million kilometers, which is not believable. How
Right.
is the sun attracting the earth when it is so far away?
Right.
Like what, since you can't see the force, how is it happening? That's the question. Nobody
Right.
would believe him if he said that yes, the earth is attracting the moon and the sun is attracting the earth. How? That is the question that everybody would ask, right?
Right.
So in order to explain the how, he has come up with the concept of field. He and other scientists also later came up with the concept of field because it explains how bodies affect each other at a distance. Action at a distance. How is that happening? The reason it is happening is because the principle of gravitational field is that any mass m1 creates a vector field in space all around it. At every point, there is some field vector that has been assigned because of this mass,
Right.
right?
Yeah.
If there are multiple masses in the universe, let's say another mass here, that will also create its own vector field at that point.
Right.
This also creates its own vector field. Ultimately, when you have many masses, eventually each point, due to all the masses, will have a net field at that point, right?
Right.
And the force that another mass experiences here will be dependent on the value of the net vector field at that point. So the whole process of gravitational attraction has been broken down into two parts. Instead of happening in one step, he is saying that it happens in two steps. Every mass creates first a vector field, and then it's the field that exerts the force on the mass present there.
Right.
So the creation of the vector field due to gravity throughout the universe is what helps you push or pull objects which are so far away. Because ultimately it's the field exerting forces. The field was created by the source mass,
Right.
right?
Yeah.
So that is basically hiding or disguising the problem. The problem was, how can a mass here affect another mass here at such a distance? Now you have sort of disguised the problem by saying that the source mass created a field, and the field is what is pushing or pulling this object.
Right.
And now the real question would have been, how is the field being created?
Right.
But that question cannot be answered right now. That is beyond 12th grade level. How is the
Okay.
field being created till the end of the universe, right? That is the real question.
Right.
So that is a slightly advanced field theory, but that we'll not be worried about. But the main idea is that to explain how come bodies are pulling and pushing each other from so much distance away, you need the concept of gravitational field.
Right.
And gravitational field is a vector field. By vector field, I mean each point in space is assigned a vector called the E vector.
Right.
And this E vector is coming due to some source mass. The mass that creates the field is the source mass. And if there are multiple masses, then obviously there will be multiple fields at that point, and the total field, resultant field, will be the vector sum. Right?
Right.
So that is your basic field idea. Then comes the idea of gravitational potential energy. Gravitational potential energy is basically how energy is stored in the gravitational field, and we can understand it on the basis of work done. So if you take m1 and m2, two masses which are at a distance r1, and they are taken from this position to finally this position r2 distance away, right?
Right.
However, when you took them along this path, maybe you were at one moment you were here, which was at a distance r, and you moved a little tiny distance dr, right?
Right.
This mass is fixed, m2 is moving, right?
Right.
Now, obviously, you should realize that because of force of gravitation being proportional to 1 over r square, the value of the force which pulls the mass m2 towards mass m1 is always changing its magnitude, right?
Right.
At the location r, the force would have been g m1 m2 by r square pulling it back, right?
Right.
So if suppose I pulled m2 from here to here, then I have to exert an equal and opposite force F, right?
Yeah.
I could exert a force F external which is greater than the force of gravity. But if I do that, then I will accelerate the mass, right?
Right.
If I accelerate the mass, the kinetic energy of the mass will change when it finally reaches here.
Right.
So what I'm going to do is I'm going to pull m2 really slowly, keeping its velocity close to zero, and
Right.
pull it from here to here. In that case, my external force must be equal to the Fg, right?
Right.
At all moments, my external force must be equal to Fg, and Fg obviously keeps changing at every point, right?
Right.
So I have to keep adjusting my force in such a way that the no acceleration happens on m2, and it is going from here to here without a change in kinetic energy,
Right.
right?
Yeah.
Slowly I'm bringing it there. So work energy theorem, if I apply, I'll say work done by external force plus work done by gravity should be equal to change in kinetic energy, which is zero, we are saying, right?
Right.
So work done by gravity is coming out to be negative of work done by external force, right?
Right.
And my external force is actually equal to the force of gravity at any given point, right?
Right.
And work done by external force will be calculated by doing R1 to R2. What is my external force dot dr? So external force is same as g m1 m2 by r square, right?
Right.
Do you understand what I'm saying?
Yeah.
External force is equal to the Fg force, and it is doing positive work, right?
Right.
So I'm going to get negative g m1 m2 common outside, and 1 by r square integral is minus 1 by r from r1 to r2, right?
Right.
So you're getting work done by gravity is coming out to be negative g m1 m2, and this becomes 1 by r1 minus 1 by r2, right?
Right. Yeah.
Notice that 1 by r1 minus 1 by r2 is a positive value.
Right.
So the work done by gravity is total coming out to be negative,
Right.
which should make sense
Yeah.
because gravity was pulling it this way and it was going that way.
Yeah.
Work done by gravity is coming out as negative, and obviously then work done by external force is coming out to be positive, which is simply g m1 m2 1 by r1 minus 1 by r2, right?
Right. Yeah.
Now you have to think about my situation. I have done this much positive work to pull it from here to here, right?
Right.
So obviously I have spent some energy, some of my energy, right?
Right.
Where did my energy go?
It got stored as the gravitational potential energy.
So otherwise, if my energy vanishes, then that is weird because then total energy is not conserved.
Right.
I have done some of my work, some work I did. This much work was done by me, so my internal energy has reduced.
Right.
So where did this amount of internal energy go? It got stored as potential energy of in the gravitational field.
Right.
So now that we understand intuitively that there should be some potential energy stored, what we can say is because gravity is a conservative force, work done by gravity is minus delta U gravity.
Right.
This is from work energy chapter for any conservative force.
Right.
So since it is minus delta Ug, we can say minus delta Ug is equal to minus of this. So we'll
Right.
say delta Ug is equal to G m1 m2 by r1 minus G m1 m2 by r2, right?
Right.
This is delta Ug will be final minus initial, so u2 minus u1 is coming as this, right?
Right.
Which means my potential energy function should be negative G m1 m2 by r, right?
Right.
Do you understand why it has to have a negative sign ahead?
Yeah.
Because my u2 minus u1 is coming as this minus this. So obviously u2 should be this part, right?
Yeah.
So it has to have a negative sign.
Right.
So by this derivation, we have understood how to define the potential energy due to gravity for pair of masses. This is a pair of point masses separated by a distance r. And this is the expression for potential energy due to gravity.
Right.
And we also know work done by gravity is negative delta Ug, right?
Right. Yeah.
So this is super important because this formula helps us avoid having to integrate all the time to find work done by gravity, right?
Right. Yeah.
If you know the expression for potential energy, you just have to take the difference of the two potential energies. You don't have to integrate F dot dr.
Right.
So that is super important. And now that we have defined potential energy between two pairs of masses, m1, m2 separated by r, if there is a collection of masses more than two, we have to take each pair and its own potential energy and accordingly sum up the whole potential energy of the system.
Right.
Do you understand what I'm saying?
Yeah.
All the pairs possible you have to take,
Right.
right?
Yeah.
So that will give you the total gravitational potential energy of the system. Every time you have to do this, R is the separation between the masses, M1, M2 are the values of the masses, right?
Right. Yeah.
So now in the same situation as before, we saw that this was the situation. It was at R1 distance first, and later M1 and M2 were at an R2 distance, right?
Right.
We had a U1 value here and a U2 value here. U2 was minus G M1 M2 by R2, and U1 was minus G M1 M2 by R1, right?
Right.
So obviously, if I kept the source mass here as fixed and I was moving this mass from here to here, I have seen that there is a delta U that happened.
Right.
U2 minus U1. There is a delta U that happened as I moved it from here to here.
Right.
Now, what we will say is we'll define a new concept which is called gravitational potential, which is not very different from gravitational potential energy, which is just a little different. We'll say that anytime you move a mass from some position to some other position, the gravitational potential energy potential of that mass will also change, just like the gravitational potential energy will also change, right?
Right.
For example, we are now going to define a quantity called delta V, which is equal to delta U by the mass that was being moved.
Right.
So M2 was the mass that was moving. Right?
Right.
So as a result of moving from point P1 to point P2, the potential energy has changed, delta U, right?
Right.
We are going to define the change in potential as the delta U by M2. So this comes out to be minus G M1 minus G M1 by R2 minus plus Gm1 by R1, right?
Right.
If you calculate delta U by M, that is what should come.
So just like with the gravitational field, is there a reason why we are using this gravitational potential?
There is a reason. First, we'll understand what it is, then we'll come to
Okay.
the reason.
Okay.
This is what we are getting, and then we are going to say V2 minus V1 is this. And so accordingly, we can see what pattern is there. So we can define B as minus Gm by R, right?
Right.
This is my expression which will make it fit this definition.
Right.
Are you understanding what minus sign has to come?
Yeah.
Because according to delta U by M2, this is what came as delta V.
Right.
So this must be the V2 and this must be the V1, right?
Right.
So it has to be a negative sign.
Right.
So what we have gotten is that due to mass M1, there is a potential at this point V1, which is minus G M1 by R1. And there is a potential at this point V2, which is minus G M1 by R2, right?
Right. Yeah.
The mass that was moving does not come in the equation. The mass that comes in the equation for potential is the source mass again.
Right.
So what we are getting now is that a source mass, if you place here, it creates potential at all of these points, right?
Right.
If the distance here is R1 and the distance here is R2, the potential at these 2 points is this, right?
Right.
Now, this is very similar to the field concept. The source mass was creating a field also at these two locations, right?
Right.
The only difference is that field was a vector quantity that was being assigned, and this is a scalar quantity that is being assigned.
Right.
Potential is a scalar because potential energy was a scalar. So think of E as a vector field created by mass m, created by mass m, which is the source, and think of V as a scalar field created by mass m.
Okay. Right. Right.
Both of these are actually similar things, like they are very closely related because it is creating a field. That's why it was exerting a force. That's why work was done. That's why potential energy was changed. That's why we are getting potential, right?
Right.
The only thing is that this was a vector field, this is a scalar field. The reason we are defining this is because sometimes in certain situations, it is easier to find the potential rather than the field.
Okay.
If there are continuous bodies, multiple masses are there, and I want to find P at this point, P, field and potential. Obviously, you should realize that field is much harder than potential.
Right.
Because for field, you will have to take vector fields from each of the masses and add up 6 vectors,
Right.
which will be annoying to do.
Right. Yeah.
But for potential, you just have to add up numbers. These are scalars.
Right.
So if you know the distance from P from each of these masses, you just add up the numbers minus gm1 by r1 minus gm2 by r2 minus gm3 by r3. And you get
Right.
easily potential at that point.
Right. Yeah.
So the scalar field is easier to calculate. That's why we are doing it. And later you will see that the advantage is that once you find the potential, you can figure out the field because there's a connection between the two quantities.
Right.
So an
Uh,
indirect way of finding the field would be to first find potential and then from potential find the field.
right. Sir, in that example you showed before with the multiple particles, is it possible to find the field by taking the center of mass of all those particles and then checking?
No, gravitational field is not necessarily going to be from the center of mass, Like, I mean, that's the expectation, but it doesn't have to be the reality.
Okay.
Like, see, it is likely that it will be from there, but the strength of the field and all, you will have to understand that, right? Like
Right.
ultimately, it is sum of vectors. If even if the center of mass was here, are you sure that the field strength would be dependent on this distance? That is not
Right.
guaranteed.
Right.
You understand what I'm saying?
Yeah.
If you add, if you take a simple case, if it is a symmetric case and forces are gm1 by r1 square and gm2 by r2 square, maybe the net field is in this direction,
Right.
right?
Yeah.
But the net field vector here would be the cos component of this cos plus this cos, right?
Right.
It is not necessary that it will be equal to the g from here, the r square distance, right?
Right. Yeah.
So you cannot make assumptions like that.
Okay.
You have to actually find out the field and see what comes. You can't really assume that you can replace it with one mass and it will magically work out to be the sum of the vectors,
Okay.
right?
Right.
So now what is the connection between field and potential that we can easily establish? We can say that work done by gravity will be negative delta U due to gravity. Work done can be written as force of gravity dot dr if you go from r initial to r final.
Right.
And this can be written as minus the definition of delta V was delta U by M, right?
Right.
So this is minus M delta V.
Right.
And the force Fg due to gravity can be written as Me.
Right.
You can say Me dot dr Ri to Rf
Right.
is equal to minus M delta V. M can get cancelled. You have delta V is equal to minus integral Ri to Rf E dot dr.
Right.
And this delta V can be written as integral Ri to Rf dV is equal to minus integral Ri to Rf E dot dr. Right?
Right. Yeah.
Now you can write the non-integral form, which is dV is equal to minus E dot dr.
Right.
This is the differential form, this is the integral form, which connects change in potential to the field at that location.
Right.
These two equations, mathematically, it is easy to understand, but you need to understand what it really means physically. So, from a physics point of view, if a particle is moving from here to here, and let's say this was my Ri, and this was my Rf, right?
Right.
What we are really saying is if you go from this point to this point, what is the delta V, right?
Right.
And you are following this path, right?
Right.
Delta V is minus integral E dot dr, where maybe if you were at this position, r vector, and your dr was this much, dr, right?
Right.
And at this point, your field could have been something like this E.
Right.
Particle has moved from r to r plus dr,
Right.
right?
Yeah.
If the particle moves from here to here, you take the field vector dot product with the dr vector and you integrate from initial to final position. So you have to add up all of these small motions, right?
Right.
As you cover the whole distance of the path by slowly taking E dot dr here, E dot dr here, E dot dr here, E dot dr here, and like that, right?
Right.
You will end up with a total change in potential from here to here.
Right.
So why is this form important? Because it is not guaranteed that if you go on a big path like this, field is always constant, right? Field doesn't have to be always constant.
Yeah.
Field could vary at different points on the path, right?
Yeah.
Obviously, you can see that the dr vector is also changing its direction and all.
Right.
So at every small portion of the path, the E dot dr gives you the negative dv there, right?
Right.
If you move from here to here, what is the change in potential? It is equal to E dot dr.
Right.
Similarly, if you move from here to here, what is the change in potential? It is equal to E dot dr.
Right.
So the integral form is saying to find the total change in potential when moving from here to here, break down the path into small paths of dr length, right?
Right.
Calculate the E dot dr value in each small portion. And E could obviously have a different direction at different points.
Right.
If you add up all the negative E dot drs from the initial to the final end point of the path, then you will get the total change in potential.
Right.
Are you understanding what I'm saying?
Yeah.
Now, what does this mean on a microscopic path? On a small path, it means that if I go only from r vector to r plus dr vector, right?
Right.
So this is your small dr vector, right?
Right.
If it was just a small path, we can assume field is uniform over that small path, right?
Right. Yeah.
Because you have not moved much. So field can be assumed to be constant over this small interval, right?
Right. Yeah.
So in that case, you can say change in potential from here to here is equal to negative of E dot the dr vector.
Right.
And obviously it's a dot product, so it depends on the angle between the E vector and the dr vector.
Right.
So that is the meaning, and this equation will become super important because we'll use it to figure out the field from the potential information. If you know the potential, you can connect it to the field.
Right.
Because what we can say is dv is equal to minus ex I cap plus ey j cap plus ez k cap dot product with dr. Dr can be written as dx I cap plus dy j cap plus dz k cap, right?
Right.
This is the general field at that location. This is the dr vector as you move a small distance.
Right.
So the change in potential is becoming simply minus ex dx minus ey dy minus ez dz, right?
Right.
And now, how do I find out ex ey ez? What you can say is, let's move on a path from xyz to x plus dx yz. So think about it. This is a path where only the x part has changed, right?
Right.
Dr vector will be simply dx I cap,
Right. Yeah.
because there is no change in the y and z, right?
Right.
So if you move along the x-axis such a way that you move the small distance dx and nothing in y and z, then obviously what we can say is that the dr vector is dx I cap, and when you do the dv calculation, dy and dz are 0.
Right.
So you get dv is minus ex dx,
Right.
and then ex is coming out to be minus dv by dx, right?
Right.
Now here you have to remember that y and z are constant, right?
Right.
Because when you moved on your path, you did not change the y and z coordinates.
Right. Yeah.
So if you know the value of the potential as a function of x, y, z in space, suppose somebody gave you the potential due to the source mass at any point in space in that region, right?
Right.
Then we have a direct way to find Ex, right? We have to do minus dV by dx, keeping y and z constant.
Right. Yeah.
Keeping y and z constant means you are doing something called a partial derivative of v with respect to x.
Right.
Why partial derivative? Because technically v could vary with all three coordinates. But right now only the x coordinate is changing, right?
Right.
Y and z coordinates are not changing. So you will get the x component of the field by doing the negative. Ex is negative dou v by dou x, which is a partial derivative of v with respect to x.
Right. Okay.
In a similar way, you can find Ey also, but this time you'll have to go a small distance in the y direction, keeping x and z constant,
Right.
right?
Yeah.
If x and z is constant, these two terms will disappear and you'll get Ey is equal to minus dou v by dou y, and
Right.
Ez is equal to minus dou v by dou z, right?
Right.
So the advantage of this thing is that if you know v function, then we can easily find the electric field or gravitational field, because it is minus dou v by dou x I cap minus dou v by dou y j cap and minus dou v by dou z k cap, right?
Right. Yeah.
And that is much easier than trying to integrate the charge distribution or mass distribution to find E directly.
Right.
If there was a complicated mass distribution, finding potential is probably going to be much easier than finding E, right?
Right.
And if you are able to find the V as a function of x, y, z, then E is automatically known by this relation.
Right.
Are you understanding?
Yeah.
Okay. Then once we know the connection between V and E, then we can start by looking at the basics of the derivations of field and potential. We'll start with the potential derivations first and then go over to the field derivations. All of the derivations you have to be able to do yourself without looking at the book. Okay?
Right. Yeah. Okay.
So even if it is seeming confusing right now, you have to reread it, cover the book, try it yourself again. We will discuss all of this in the next class. So we can do the class tomorrow also if you want, but
Okay.
we have to do it properly because immediately in the next chapter, chapter 29, you have to use the same things again.
Right.
Electrostatics, all the derivations are the same because the charge Coulomb's law function is exactly the same as the gravitational law thing.
Right.
So literally everything that we are studying here will be the same. Okay. So
Right. Okay.
you have to do it properly once so that you can also derive it yourself if required. So go through the theory once more for the derivations part. We can do the class tomorrow if you need to discuss it tomorrow. Otherwise, whenever you are free. And we'll finish the derivations in the next class of potential and field.
Right.
After that, after you know this, then we have to discuss your planets and satellites, energy, escape velocity, and finally Kepler's laws.
Right.
That will cover the whole chapter. So most important things are this section, all of the derivations. So try to go through it once more, see if you're able to get it. Otherwise, we'll discuss in the next class and finish it.
Right.
Okay.
Okay.
Remember that it is for two chapters that you are doing it right now, for gravitation also and electrostatics also. So super important.
Okay.
Fine. We'll discuss further in the next class.
Okay. Thank you, sir. Bye.
Bye.